Every day, people are hurt and killed by fire. A lot of property is destroyed, too. Now, some of these fires happen at work, and some of them at home. I'm the fire marshal at this plant, and so far, we've got a pretty good record where fire safety is concerned. I think one reason for our good record is the amount of training we do in fire prevention and in firefighting. You see, if everyone's trained in how to handle fires, you can prevent a lot of them. And for the fires that do get started, knowing the correct response helps avoid the injuries and damage that fire can cause. Fire safety at the plant is my main job, but I've found that all the things we teach here apply to fires at home as well. We're going to talk about several different subjects relating to fires and fire safety. First, we're going to see what fire is. We'll talk about the different type of fire extinguishing agents and the types of fire equipment you'll find both at work and at home. We'll see the correct way to respond to a fire emergency and learn about fire hazards and how they can be reduced or eliminated. This kind of training makes my job a lot easier, but it's just as important to you. You see, fires don't just happen on the job. They also happen in people's homes. Fire is a combination of 4 elements: fuel, heat, oxygen, and a chemical chain reaction. Whenever these 4 elements, called the fire pyramid, are present in the right proportions, you've got a fire. When any one of the elements is removed, the fire goes out. Fires are dangerous in 2 distinctly different ways. First, they generate a lot of heat. There's always the risk of burns. Secondly, as fuel's consumed, fires release smoke and toxic gases that can suffocate someone or poison them. Now, one of the worst things about fire is that it can spread fast. When you've got a fire, you have to get it out quickly before it has a chance to get bigger. Usually, if you catch a fire early enough, you can put it out with a portable extinguisher. Fire extinguishers come in 4 basic types. There's water, foam, dry chemicals, and gases. Each type works by attacking one of the elements of the fire pyramid. Water quenches a fire. It removes heat from the combination. When enough heat is removed, the fire goes out. Foam works in a different way. The foam makes a sticky blanket of small bubbles that smothers the fire. Foam blocks out oxygen, so the fire goes out. Dry chemical extinguishers attack the chemical reaction itself. By interrupting the reaction, the chemical keeps the other elements of the pyramid from combining with each other and burning. Extinguishers that use gases can work in 2 different ways. Some, like carbon dioxide extinguishers, displace oxygen and smother a fire. Other gas-type extinguishers, like halon, work directly on the chemical reaction. A little later, we'll see just how each of these extinguishers is used, and we'll learn which kinds of extinguishers are suited for different kinds of fires. But for now, it's important that you know what fire is and how it burns, and how different kinds of extinguishers work to put fires out. We've said that fire is a combination of 4 elements: fuel, heat, oxygen, and a chemical reaction. We've also seen how fires are put out by removing one of these elements. You can remove the fuel. You can remove the heat. You can eliminate oxygen, or you can interrupt the chemical reaction. If you remove any one of these elements, the fire goes out. As we talk more about fire safety, we'll return to the fire pyramid from time to time. It's a good way to understand how a fire burns and how it can be extinguished. In a few minutes, we'll be back to discuss the 4 different classes of fires, and we'll see which extinguishing agents are effective for each class. Until then, work through section 1 of your text and ask your instructor about any questions you might have. So far, we've learned what fire is, a chemical reaction between fuel, oxygen, and heat. And through the fire pyramid, we've seen how different kinds of extinguishing agents work. Each one removes a different element from the pyramid. Since different kinds of extinguishers act in different ways, it's important to know which kind of extinguisher is best for a particular type of fire. To decide on the type of extinguisher you need, first you have to know what kind of fire you've got. Fires are divided into 4 different classes: A, B, C, and D, according to what's burning. Class A fires are ordinary combustible materials like wood, paper, or coal, anything that leaves an ash. Class B fires are ones that involve burning liquids or gases. Oil fires, burning gasoline, and propane fires are all Class B. Class C fires are ones with energized electrical equipment. A burning motor or transformer or even an electrical outlet is a Class C fire until you turn off the power. Then it'd be a Class A or Class B depending upon what was burning, solids or liquids. Class D fires are fires involving combustible metals, metals like magnesium, titanium, and sodium. Where these metals are used, fires are especially hazardous. They burn at extremely high temperatures and are hard to put out without a special extinguisher. The other 3 classes, A, B, and C, can be put out with one or more of the extinguishing agents I mentioned earlier: water, foam, dry chemicals, or gases. Well, let's see some fires now and see which agents are most effective for each kind. Here's a Class A fire. One way to put it out is with water. Large Class A fires are handled with fire hoses. Water quenches the fire by cooling the fuel and smothering the flames with steam. Smaller Class A fires can be put out with a portable pressurized water extinguisher. These extinguishers are identified with a green triangular A. That means they're effective for Class A fires only, fires involving common combustible solids like wood or paper. Multi-purpose dry chemical extinguishers will also put out small Class A fires. This one is rated ABC, so it can handle small fires with combustible solids, liquids, and even electrical equipment. Here's a dry chemical extinguisher being used on burning oil, a Class B fire. Covering the surface of the liquid with the chemical puts the chemical in direct contact with the base of the flames and gives it a chance to break up the chemical reaction of the fire. Fire hoses can also be used on flammable liquid fires. Using a wide spray pattern helps the water cool the surface of the liquid without splashing the flames into other areas. The cloud of steam helps smother the fire, too. Foam extinguishers put out burning liquids in a different way. A blanket of foam over the surface smothers the flames. CO2 also smothers a Class B fire. CO2 works best on burning liquids when the gas can settle at the base of the flames and displace the air. CO2 extinguishers are rated BC. That means they're intended for burning liquids and gases and for electrical fires. Now, if this switchgear started burning, I could cut the power and put the fire out with this extinguisher, and there wouldn't be any water or chemical residue that could damage this stuff even more. When you've got an emergency, though, you're not concerned with trying to save wiring that's already burned up. If you have a dry chemical extinguisher, use it. This transformer's junk now, but the fire's not going to spread. For fires in energized electrical equipment, CO2 or dry chemical is your best bet. But the first thing to do is cut the power if possible. That removes the source of ignition, so the fire won't be as likely to flare up again after you put it out. If you can cut the power, that removes the fire from the Class C category. It no longer involves energized electrical equipment. Then the fire will be either Class A or Class B, depending on what's burning. So, on a large fire, you could use a fire hose once the power's been turned off. It's only in very exceptional circumstances that hose streams are used on energized electrical equipment. Water can conduct current upstream to you. Water is sometimes used on energized electrical equipment. It's used when lives are at stake and there's no other way to cut the power or put the fire out. When that's the case, a fireman can use two precautions to protect himself from electrical shock. He gets as far away as possible and uses a wide spray pattern on the hose nozzle. Both of these factors affect the electrical conductivity of the water stream. The farther away you are and the wider the spray pattern, the less likely you are to get shocked. Class A, B, and C fires are the most common types most of you will encounter. However, someday you might work in a place where combustible metals like sodium, titanium, powdered aluminum, or magnesium present special fire hazards. These metals burn hot, some of them up into the thousands of degrees. Now, I've got some magnesium ribbon here. It's a good example of a combustible metal, so let's see how it burns. Magnesium has a pretty high ignition temperature, but once it starts, it burns white hot. The worst thing about combustible metals is that they're very difficult to extinguish. You have to use a special extinguisher because water and some of the other conventional extinguishing agents can actually make a metal fire burn hotter or even explode. A Class D fire extinguisher will be labeled with a sticker like this. Usually the extinguishers are located only where there's a special hazard from flammable metals. In fact, there are different kinds of Class D extinguishers for different kinds of combustible metals. An extinguisher that works on magnesium fires might not be appropriate for sodium or lithium. At any rate, if you don't have the right kind of special extinguisher on hand, smother the fire with sand. And whatever you do, don't use water. You might end up with an explosion. So far, we've talked about each of the four classes of fires, and we've seen what extinguishing agents are most effective for each class. Class A fires involve combustible solids like wood, paper, and coal. They're put out with water or with a multiple-purpose dry chemical extinguisher. Class B fires, ones with burning liquids or gases, can be put out with dry chemical, CO2, or even a fire hose with a fog nozzle. Electrical fires, Class C, are put out with CO2, with dry chemical extinguishers, or in special circumstances with water. Class D fires involve combustible metals like magnesium. Only special Class D extinguishers can be used on these kinds of fires. You've seen what each of these extinguishers can do. What you need to know now is how to operate each of the different kinds. Pressurized water, foam, dry chemical, and CO2. In a few minutes, we'll be back to take a close look at how each of these extinguishers is used to put out a fire. Until then, look through Section 2 of your text for more information about the four classes of fires. While you're at it, think about this question. Out of all these different kinds of extinguishers, which one would you prefer to have at home for the most complete protection? Out of these 5 extinguishers, could you choose the one that would provide your home with the greatest protection? Would it be dry chemical or CO2? How about pressurized water? Or maybe foam? Well, if you picked this one, you made the correct choice. It's a multi-purpose dry chemical extinguisher. It's effective on Class A, B, and C fires. That provides protection from every kind of fire you're likely to encounter at home. And that's why I keep 2 of them at my house. At work, you probably see fire extinguishers hung on the wall, like this one. This station's equipped with a CO2 extinguisher because right here, the greatest fire hazards are flammable liquids and electrical fires. At other locations in the plant, where hazards are different, you'll find dry chemical extinguishers, pressurized water extinguishers, or foam. We're going to talk about each of the extinguishers you see here. You've already learned what kinds of fires each is good for, so now we're going to see how each extinguisher is made and how they're used. We'll start with dry chemical extinguishers. I've got 2 different kinds of dry chemical extinguishers here. This one's an ABC stored pressure type. The other one's only rated for B and C fires. It has a different chemical inside. It also has some features that require a slightly different technique of operation, which we'll see in a minute. First, let's take a look at the stored pressure type. This one is a cylinder filled with a chemical and pressurized with nitrogen gas. On top is a gauge that shows the amount of pressure in the cylinder and a control handle that regulates the flow of chemical through the hose. Let's see how it's used on a Class A fire. The first step is to twist the pin and pull it to release the control handle. Test the extinguisher with a good strong blast, and then approach the fire with the wind at your back. A full blast of the extinguisher may cause the fire to flare up at first because of the rush of air that follows the stream. But squeezing the handle carefully allows you to put the chemical right where it's needed without causing a flare-up or wasting chemical. Once the fire has been knocked down, you have to poke apart and get the burning embers underneath. That's how to make sure the fire won't start up again. Before we go on to see how the rest of these extinguishers are used, I want to mention some general points that apply to any fire extinguisher. First, make sure it's full before you go in. Now, on this kind of an extinguisher, there's a gauge to show the amount of pressure in the cylinder. It should read in the full range. Even if it does, it's a good idea to have another extinguisher for a backup just in case the first one doesn't work. Next, with any extinguisher, test it before you approach the fire. Then approach slowly, using the extinguisher's stream to protect yourself from the flames. Don't get too close at first, because a fire will almost always flare up with the first burst of the extinguisher. Use a side-to-side motion to sweep the agent across the base of the flames. With any Class A fire, you'll have to go for the remaining embers after you get the main part of the fire out. Once you're done, back away from the fire. You might get a reflash. That's when the fire flares up again after you get it out. And you don't want to have your back turned when that happens. Okay, we've seen the ABC multi-purpose extinguisher at work. Now we're going to move on to another kind of dry chemical extinguisher, the BC cartridge type. There are 2 main differences between this one and the ABC stored pressure type we saw before. One difference is the chemical inside. This one's only good for Class B and C fires. It's not effective on Class A fires. The other difference is the way the cylinder is pressurized. This cylinder's always pressurized, while this one's not pressurized until you puncture the CO2 cartridge on the side. There's some advantage to this design. When you puncture the cartridge, the rush of gas into the cylinder stirs up the chemical and makes sure it'll all come out and not lie caked on the bottom. Well, let's watch this extinguisher go to work on a Class B fire. The first thing to do is unhook the hose and puncture the CO2 cartridge by pushing the lever. Then, test the extinguisher and advance from the windward side. Sweep the chemical across the base of the flames, being sure to cover the entire surface. When the fire's out, back away and watch for a reflash. Well, that's one way to put out a Class B fire with a BC dry chemical extinguisher. You can also use this one, a CO2 extinguisher. The cylinder's filled with carbon dioxide. You control the flow with this handle, which has a locking pin. The gas comes out through the hose and the horn. That's how you direct the stream. Let's see how it works on a Class B fire. First, twist the pin and pull it out. That frees the control handle so you can test the extinguisher. Then, approach from windward and cover the entire surface of the liquid with CO2. When the fire's out, back away, just like before. When carbon dioxide is released from pressure, it expands rapidly and gets very cold. It actually creates frost on the horn as it comes out. Now, if you're holding the horn up here, you'll get kind of frostbitten. So handle it by the grip. That's what it's for. Well, so far we've seen 3 different kinds of extinguishers. ABC dry chemical, BC dry chemical, and of course, CO2. All of these extinguishers can handle at least 2 different kinds of fires, and the ABC extinguisher can handle 3 types. The next extinguisher we're going to look at is a little bit different. It's effective on only one kind of fire, Class A. This is a pressurized water extinguisher. The cylinder is filled with water or antifreeze and pressurized with either air or CO2. The gauge at the top tells you how much pressure is left inside. Let's see how it works on a Class A fire. Twist the pin, pull it out, and test the extinguisher by squeezing the control handle on top. Aim the water stream at the base of the flames and slowly advance as the fire begins to die down. Remember, water extinguishes a fire in 2 ways, by smothering it with steam and by removing heat. So hit the hot spots first. When the fire's died down, poke it apart and stir the ashes. This helps you uncover any hot spots underneath and separates the embers so the fire will be less likely to start up again. Move around so you can direct the stream right where it needs to go. It's often helpful to place your finger over the end of the nozzle to break up the stream into a spray pattern. This enables you to cover more area with the spray and prevents spreading burning embers with a solid stream. All of the extinguishers we've seen so far are currently manufactured and are widely used in industry. We've got one more type to cover, foam. Now, this is kind of an antique. They're no longer manufactured, but since they're still widely used, we're going to cover it anyway, just in case you've still got these around where you work. The cylinder has 2 chemicals inside in separate chambers. When you turn it upside down, a lead stopper falls out and allows the 2 chemicals to mix. The reaction makes foam and CO2. Enough CO2 pressure is built up inside to force the foam out through the nozzle and onto the fire. Here's the problem. If you turn one of these upside down and foam doesn't start coming out immediately, you're holding a bomb in your hands. Pressure's building up inside, and soon it'll be enough to blow the cylinder apart. That's why they're no longer manufactured. If you're holding one of these and foam doesn't come out, throw it as far as you can and take cover. You're going to have some shrapnel flying around. Whatever you do, don't hold it so the top or bottom of the cylinder is pointing at a part of your body. They haven't perfected head transplants yet. Well, even with all their drawbacks, though, foam extinguishers are extremely effective at putting out Class B fires. Their main advantage is that the foam creates a blanket over the entire surface of the liquid, so there's no way it can reflash on you. So, let's watch a demonstration and see how it works. To get this extinguisher going, all you have to do is turn it upside down and wrap it once on the deck. As soon as the two chemicals mix, foam should start streaming out of the nozzle. When you're fighting a liquid fire in a container like this one, avoid directing the stream right onto the surface of the liquid. That'll only spread the fire by splashing flaming liquid into other areas. The best way is to bounce the stream off the far wall of the container. The foam will gradually float back toward the near wall. As it covers more of the surface of the liquid, the fire's confined to a smaller area. Finally, when the entire surface is covered, the fire goes out, and the foam blanket keeps it from reflashing. Well, that pretty much takes care of all the types of portable fire extinguishers you're likely to use. We've seen how each of these is operated. ABC dry chemical, the stored pressure type, BC chemical, the cartridge type, CO2, pressurized water, and finally, foam. Earlier, we learned about the 4 classes of fires and which extinguishers are effective for each class. The multi-purpose dry chemical extinguisher is effective on Class A, B, and C fires. This dry chemical extinguisher is effective on Class B and C fires only. CO2 extinguishers also work on Class B and C fires, while pressurized water extinguishers are for Class A fires only, and foam extinguishers are rated for Class A and B fires. These 5 types of extinguishers are your basic portable devices for fighting fires. Although we've shown you how they work, the only real way to learn how to use them is through practice. If you have a practice area at your facility, you'll get a chance to try out the types of extinguishers used where you work. Before going on to the next part, read through Section 3 of your text. It has more detail on the use and care of each of these extinguishers. When we come back, we'll take a look at some other kinds of fire extinguishing devices, built-in fire extinguishing systems. In the last part of this program, you saw how several different kinds of portable fire extinguishers are used. We're going to look now at a few other kinds of fire extinguishers, but they're not the portable kind. The fire extinguishing systems we're going to see now are built into the design of the plant. Now, some of these systems, like this fire hose station, are operated manually. Others, that we'll see later, are automatic systems that go off when their sensors detect a fire in the area. Now, you're all familiar with fire hoses, even if you've never used one. At your plant, you might have fire hose stations like this one, but even if you don't, you probably have fire hydrants or some other kind of fire department connection. This hose station's equipped with a hydrant, right here, and a wrench to open its valve. One hose is already coupled to the hydrant. On the end of it is this fog nozzle. A nozzle that has a variable spray pattern. Works something like the nozzle you have on your garden hose at home. There's another hose right up here, and this one can be coupled to the hose down here. There are a few other things here. Here's another type of nozzle. This one's for straight streams. This is a spanner wrench. It's for disconnecting the hoses. Now, don't use this for tightening hoses. They should only be hand tight. To use a hose station like this one, you unreel the hose all the way while someone else opens the hydrant valve. Now, this kind of hose is stored flat, so you have to unreel it completely to create a clear path for the water. Then you can control the stream by twisting the adjustment on the fog nozzle. Let's go to the demonstration area now and see how a fire hose is used on a real Class A fire. As the nozzle man approaches the fire, he stays low where the best air is and uses a wide spray pattern to protect himself from the heat of the flames. The wide pattern diffuses the spray over a fairly large area of the fire and doesn't knock burning fuel into the surrounding area the way a straight stream would. Once the main part of the fire is out, the nozzle man directs the stream onto the hot embers remaining underneath, hitting the hot spots so the fire won't be likely to start up again. As you've just seen, fire hoses can be very effective tools for putting out Class A fires. The most important thing to consider is the spray pattern. A solid stream of water can actually spread a fire by pushing burning fuel into other areas. But a fog nozzle, like this one, can be adjusted so that its stream can be either wide or narrow. A wide stream can be pretty effective and helps protect you from the heat of a fire. A narrower stream is used when you have to direct the water into a narrow opening or when you need additional distance. Remember, fire hoses are for emergencies only. They're not for washing down equipment or rinsing the deck. You can find something else for those jobs. Fire hoses are only one kind of built-in fire extinguishing system. They use water and they're operated manually. Let's take a look at some other kinds of systems now. Systems that use water and are usually actuated automatically. The building you work in may be protected with a sprinkler or deluge system. Both systems have a network of water pipes leading to spray heads on the ceiling. When a spray head senses heat, it opens, sending water down to extinguish the flame. On sprinkler systems, each head opens individually. Water flows only from the spray heads directly exposed to heat. Deluge systems are different. When the sensor's exposed to heat, all the heads go off, flooding the area with water. The basic difference between sprinkler and deluge systems is that on a sprinkler system, only the heads directly exposed to heat are going to open up. Now, deluge systems open all their heads at once and flood an entire area. Most deluge systems can also be actuated manually. Sprinklers are used where ordinary combustibles are the hazards. Usually all it takes is one or two spray heads to put a fire out. Deluge systems are for places where there's an extra fire hazard because of explosives or flammable liquids. Sprinklers and deluge systems both use water as the extinguishing agent, but that's only one of the agents used in built-in extinguishing systems. Other areas are protected with systems that use gases. For example, this oil storage room is equipped with an automatic CO2 extinguishing system. The gas comes out of nozzles overhead. All the nozzles in the room open when any one of the heat sensors is exposed to high temperatures. Carbon dioxide gas flows out of these compressed gas bottles and along the piping. 3 pressure switches are actuated here. One sounds an alarm in the control room, one stops the room's ventilation fan, and one cuts power to the pumps that deliver and remove oil. At the same time, all the CO2 nozzles go off and an alarm is sounded inside the room. The alarm is to tell you to get out of the room. These doors close automatically. And here are 2 good reasons why you don't want to be in this room when the door shuts. In the first place, it's going to be mighty hot in here. The other thing you have to think about is the breathing hazard. When the CO2 system goes off, it floods this room with carbon dioxide gas. Now, carbon dioxide is heavier than air, so it fills the room from the floor up, cutting off your oxygen supply. To go back into this room after the CO2 system goes off, you have to have a breathing apparatus, something to supply you with oxygen or air, because there's not any inside here. Not until the room's been thoroughly ventilated and tested for oxygen content anyway. Other automatic extinguishing systems that use gases can also be breathing hazards. Now, one example is halon. This building houses a gas turbine and its controls. Since explosive hydrogen gas is used to cool the turbine, a special fire extinguishing system's built in. Do not enter when alarm sounds. Halon 1301 being released. Inside the door are several round vessels filled with halon, a gas that extinguishes fires by interrupting the chemical reaction. Overhead are sensors that register any temperature increase, and nozzles that direct the flow of gas. When the system goes off, an alarm sounds, and the entire building begins to fill up with halon, a colorless, odorless gas. Halon isn't poisonous. It does displace the air in a room the same way CO2 does. But halon systems present another kind of breathing hazard as well. See, when halon's subjected to heat, as in a fire, the gas breaks down into other gases, and some of those gases are poisonous. If you have to enter an area after a halon system's gone off, you have to test the atmosphere inside first, and either ventilate the area or bring along your own oxygen supply. As a matter of fact, whenever you enter a closed-off area that's been the scene of a fire, you have to take the same kinds of breathing precautions. Fire consumes oxygen, so there may not be enough left for you. In the second place, fires create poisonous gases as byproducts of incomplete burning of fuel. So, every fire in a closed-off space is a potential breathing hazard, especially if a built-in CO2 or halon system's been actuated. The other built-in systems we've seen in this section, hoses, sprinklers, and deluge systems, all use water. Now look around your plant and see what kinds of built-in fire extinguishing systems there are. Your textbook has more information on each of the different kinds of systems. Read through section 4, and before starting up the tape again, think about this question. If you discovered a fire on the job tomorrow, how would you react? Fires don't happen on special days or to special people. For Brian and Liz, it's an ordinary morning, just like any other day at work. Brian and Liz are laboratory technicians. Here at the plant, their main job is monitoring wastewater chemistry. As part of their company's regular policy, they've been trained in fire safety, but they've never had to use their training. If there were a fire, would they respond correctly? Would you?
This is Liz from the lab. We got a fire in the screen house. Brian and I are going to go turn the power off. Call the fire department.
Personnel
Brian and Liz's training paid off. Luckily, the fire wasn't a major one, but it could have been if they hadn't responded quickly and correctly. Brian turned the power off, so the fire that started in an electric motor didn't spread to the lubricating oil in the pumps. When the fire department arrived, they went down and put out the fire in the motor. Let's go back and see step by step exactly what the correct response is. The first thing to do is report the fire. At this plant, the control room operator is the person to call. You might call a different person at your plant, but you have to call whoever's in charge of coordinating emergency action for fires. Find out who it is and how you get in touch with him fast. Now, first you identify yourself. Then state the emergency and its location. If possible, tell what kind of fire it is and whether there are injuries or damage. Finally, state the action being taken. The next thing to do is act fast. In a fire, every second counts. Fires can spread rapidly and grow too large to be put out with a portable extinguisher. If there's any live electrical circuitry involved in the fire, as it was in this case, the correct action is to cut the power. There was a Class C fire in there, but once the power was turned off, it was Class A. When more help arrived, someone went down with breathing gear and a lifeline to find the burning motor and put it out. There's no sense trying to be a hero. If there's breathing apparatus available, use it. In any enclosed place, a fire will use up oxygen in the air. That means there may not be enough for you to breathe. You could wind up passing out in a very dangerous situation. Eating smoke doesn't do you any good either, but that's hardly the biggest problem. The worst thing is the poisonous gases given off by many burning materials. Insulation or plastic pipe is especially dangerous. Some kinds release a deadly gas called phosgene when they burn. Many other common substances also release poisonous gases when they're on fire. If you do have to enter a room or building without a breathing apparatus, keep low. Since all these gases are hot, they'll rise to the ceiling. The best air is going to be near the floor. Remember though, a fire extinguisher is for fire first aid. It's not going to be big enough to put out a large fire, even if you do use it effectively. What they're best for is catching a fire early before it spreads. Another thing they're good for is escape. If you're in a room when a big fire starts, you might have to use that extinguisher just to beat back the flames enough to get out. Your life's much more important than whatever's burning in that room. We've been talking mainly about fires at work, but someday you might have to deal with a fire in your home. Fire prevention at home is our next topic. So here's a question for you to talk about when you stop to read section 5 of your text and discuss the material. Stovetop fires are pretty common. What's the best way to put them out? Think about it, and we'll be back in a few minutes with the answer. Someone's house is burning. In the United States alone, 33 people are killed every day in fires like this one. Is your home fire safe? Does your family know how to deal with a fire? Many house fires start right here in the kitchen. often when something's frying on the stove.
Hello? Oh, Susie, hi. Uh-huh. Oh, let me call you back. There's a fire on the stove.
You've just seen the best way to put out a frying pan fire, by sliding the lid across the top of the pan. Vanessa cut off oxygen from the flames, so the fire went out. Then she removed the pan from the heat. Vanessa was lucky, though. She was close enough to spot the fire as soon as it started, before it had time to spread. Sometimes people aren't that lucky. One woman was out of the kitchen when the fire started in her frying pan. By the time she discovered it, the fire had spread to her cabinets, her curtains, and her walls. She did get the fire out with a portable extinguisher, but it took a long time. Too long, as a matter of fact, because when she extinguished the fire and went to check on her kids upstairs, they were both dead of smoke inhalation. You teach your family that lives come first. If there's a fire in your house, get everybody out. Remember that smoke and hot gases rise to the ceiling, and they're just as dangerous as the fire itself. There are many places where a fire can start in a house. The kitchen's only one example. In your house, you may have other areas that are potentially just as dangerous. For example, a home workshop. Skip's first job is cleaning up some paintbrushes. It's cold, so he closes the window. That's his first mistake. Now, what's that? Not enough turpentine? Well, here's Skip's second mistake, using gasoline for cleaning. And it's especially dangerous in a poorly ventilated area. Gasoline is more flammable and potentially more explosive than any proper solvent. That's because it has a lower flash point than other combustible liquids. Let's go to the lab for a minute and see just what that means. These two dishes both contain combustible liquids, fuel oil on the right and gasoline on the left. As you can see, the fuel oil is rather reluctant to light. Gasoline, on the other hand, ignites very easily. The difference is the amount of vapor that each liquid releases at room temperature. Every combustible liquid has a certain temperature at which evaporation begins. When that temperature is reached, vapors rise from the surface of the liquid and mix with the surrounding air. It's the mixture that's important. With this combination of fuel and oxygen, all that's lacking is a spark. The liquid itself doesn't burn, its vapors do. This device heats oil gradually to measure its flash point, the lowest temperature at which a liquid gives off enough vapors to form an ignitable mixture with air. At 150 degrees Fahrenheit, 66 Celsius, the vapors flash and go out. At a temperature only a few degrees higher, the same ignition source will cause continuous burning. That means the liquid's been heated up to its fire point. Enough vapors are constantly being released to fuel a continuous flame. Gasoline has a much lower flash point than fuel oil. This is the danger of gasoline. It releases enough vapors for combustion at 45 below zero Fahrenheit. That's about minus 43 Celsius. That means that, practically speaking, gasoline is always releasing flammable vapors. Using a shadowgram like this one makes gasoline vapors visible to the naked eye. The vapor is heavier than air. It flows downward and can be poured like a liquid. Whenever they can, gasoline vapors flow downhill, which has some direct consequences on fire safety. Here's a demonstration of the point. This rag's been soaked in gasoline. Now it's being squeezed out so that it's dry enough that it doesn't release drops of liquid. The rag's then placed in the top of the apparatus, a can with a spout on the bottom. The spout allows gasoline vapors from the rag to flow out of the can and down the glass trough. As vapors flow down the trough, they mix with air, forming an ignitable mixture. Then, when a spark's applied to the bottom of the trough, the flame follows the trail of vapor back to its source, the gasoline-soaked rag. Gasoline used in your home will behave the same way. Let's see how Skip's doing with his fire hazard. Like many Saturday mechanics, Skip seems to have a hard time keeping his mind on the job. It looks like motorcycle parts are more interesting than dirty paintbrushes. Uh-oh, that cigarette could be his last. And as if the area isn't dangerous enough, he's trying to make an even more explosive atmosphere with carburetor cleaner. Not only is it extremely flammable, but the spray can spreads it out into droplets, making it mix with air even better. Let's see just how flammable it is. Now, when I said he's creating an explosive atmosphere, I wasn't kidding. So far, we know that the room's not ventilated, and it has both gasoline vapor and droplets of carburetor cleaner mixed with the air. As if that's not enough, there are batteries which release explosive hydrogen gas, piles of newspapers, and more gas and oil in the chainsaw. Over here are more flammable liquids, turpentine, kerosene, varnish, and more. What'll it be? The gasoline, the rag soaked with flammable liquids, the carburetor cleaner, hydrogen gas from the batteries, or the cigarette? Something Skip did caused this fire. We know he had created an explosive atmosphere by storing and using flammables in an enclosed room, but what was the ignition source? The key to the problem is the box where used rags were stored. Gasoline vapor, being heavier than air, flowed out of the box and pooled on the floor. Following the lowest contour of the floor, the vapors flowed out into the room next door, where they encountered the furnace pilot light. Just as you saw in the lab demonstration, once the vapors catch, the fire flashes directly back to the source, the room filled with flammable vapors. Now that we've seen the consequences, let's go back and see things as they should have been if Skip had eliminated the fire hazards in his shop. To start with, he could have removed his supply of flammable liquids and stored them outside. A shed or a metal box like this makes a good container. Old newspapers are always a fire hazard. They should be taken away for recycling. Here's what the shop looks like without its fire hazards. It's not only safer, but it has more room to work in. Jobs like cleaning paintbrushes are safest outside, and mineral spirits do a better job than gasoline anyway. When flammable liquids are used indoors, good ventilation is vital. Rags that have been used with flammable liquids have to be disposed of properly. The best way is to put them in a sealed metal container. Well, you've seen the hazards and the consequences. Unfortunately, though, there are a lot of other fire hazards in the average house, even more than you've just seen. Electrical short circuits, problems with gas lines, the list goes on and on. What's important to you is that you know the types of things to look out for and think about what you can do to make your home safer. Cleaning up flammable and combustible hazards can be very important, but there are some other positive steps you can take too. Keep fire extinguishers within reach. The best general kind to have is an ABC dry chemical extinguisher. Keep them at strategic locations around the house, areas where fires are most likely to start. Smoke detectors are also a good idea. They're sensitive enough to detect even a small amount of smoke, giving your family enough time to get out before a fire is out of control. Your first concern is for life. Practice fire escape drills with your family. Make sure they know at least 2 ways to escape from every room. Teach them that the purest air will be near the floor, since hot gases rise. When they hear the smoke detector go off, they should roll out of bed and hit the deck. 1 breath at normal height could mean the end. The fire hazards and fire protection techniques we've seen here are just a sample of many different household dangers. Your textbook has more information about fire protection at home. But remember, fires can happen anywhere, not only at home. Wherever you are, at work, on vacation, or at your house or apartment, fire can strike, and it's best to be ready. A lot of the time, fire prevention on the job depends on simple things, like cleaning up combustible trash and disposing of it properly. Sometimes it depends on following common sense precautions, like keeping ignition sources away from areas like this. Now, these are all flammable liquids. We have paint, thinner, lubricating oil, alcohol, varnish, all kinds of things all over this place. Now, wherever flammables like these are used or stored, you have a potential fire hazard. When you're dealing with flammables, you have to do 2 things. First, you have to recognize the hazard, and then you have to act to reduce the danger. Now, here we've got an assortment of flammable liquids. As you saw earlier, the main hazard is the vapors they give off. Now, what do we do to reduce the risk of fire? Well, we try to keep ignition sources away. That's why there's a no smoking sign outside this door. There are also some other precautions to take to eliminate electrical sparks. This is what you call an explosion-proof light. It's a handheld model, but there are similar ones permanently installed right overhead. Explosion-proof lights contain a light bulb inside a gas-tight enclosure. This keeps a flammable atmosphere away from the light bulb, so if the bulb breaks, the flash can't set off an explosion. Now, if the light has a built-in switch, it's also enclosed, so that the arc created by switching the light on or off can't ignite any flammable vapors or gases that are in the air. A spark from electrical equipment is only one kind of electrical spark that can start a fire. There's another kind that's often overlooked: static electric sparks. You ever walk across a rug, grab the doorknob, and get a little zap? Well, that's a static electric discharge, and it makes a spark that could be enough to ignite vapors in the air. Now, when you're working with flammable liquids, you have to worry about static discharges when you're filling a container or transferring liquid from one container to another. There's a very simple way to eliminate the risk. You remember getting zapped by the doorknob? Well, once you got that first little shock, you could touch the knob again and there'd be no shock the second time, and that's because the first discharge equalized the electrical charge between you and the doorknob. And once the charges between 2 objects are equalized, there's no possibility of a static discharge. So here's what you do when you're filling a safety can from another container. First, you touch the 2 containers together, so you equalize their electrical charge. Then keep good metal-to-metal contact while you open up and you pour. And there'll be no sparks. Now, that's how you do it with small containers. When you're filling from a larger container, like a drum, you can tie the 2 containers together with a piece of wire. That's called bonding. It works the same as touching the 2 containers together. It equalizes their electrical charges and prevents sparks. When you're loading or unloading tank cars, even stricter precautions are taken. The two containers are bound with a wire or by metal-to-metal contact, and the tank car is also grounded. Another wire is used to equalize the electrical charges between the tank car and the ground. Now, these are all ways of eliminating ignition sources in potentially hazardous areas. So far, we've covered 3 possible ignition sources: smoking or open flame, arcs from electrical equipment, and static discharges between containers. However, flammable liquids sometimes ignite without an outside ignition source, and this is called spontaneous combustion. Spontaneous combustion often happens when oily rags are thrown together in a pile. Oxygen in the air slowly combines with the oil, raising the temperature of the pile gradually. If conditions are right, the temperature gets high enough for the rags to burst into flame. Here's a situation where spontaneous combustion is very possible. The right way to store used rags is to place them in a can like this and close the lid to keep oxygen away from the rags. This kind of spontaneous combustion occurs when oily rags are kept in a place that has enough oxygen to start the reaction, but not enough ventilation to carry away the heat buildup. However, there is another kind of spontaneous combustion. It involves the reaction between a flammable liquid and an oxidizer. Now, an oxidizer is a substance that makes it easier for oxygen to combine with the fuel. Some examples are chlorine, potassium nitrate, ammonium nitrate, and oxygen. When these substances are in contact with the fuel, sometimes room temperature is high enough to start the fuel burning. Let's see an example. A pad's been soaked with a small amount of petroleum solvent. The beaker contains chlorine gas. Pure oxygen would cause the same reaction. To prevent these kinds of fires, keep oxidizers away from fuels. So far, we've been talking about flammable liquids. One of the things we talked about was how vapors rise from a liquid and mix with air. And we learned that without that mixture, the liquid won't burn. Well, solids, like coal, behave in a similar fashion. This lump of coal here isn't real easy to ignite, but if it was powdered into a fine dust and spread through the air, well, the slightest spark could set it off. That's because an airborne dust mixes with the air to create a flammable or even an explosive atmosphere. Almost any kind of dust is potentially explosive when it's dispersed through the air in the right concentration. Coal's one example. The grain dust, fiber dust, and dusts from plastics are equally dangerous. Just about anything will burn if it's ground up into small enough particles. This demonstration should show you what I mean. Here's some coal dust. It's a very fine powder that was collected from the highest elevation in the plant. It ignites very easily. When a large enclosed area is filled with an airborne dust like this, even a small spark can set off an explosion equal to tons of TNT. Wherever you have an explosive atmosphere, whether it's from dust, flammable vapors, or flammable gases, all you can do is keep ignition sources away from the area. Of course, it's best not to create the situation at all. For example, releasing this acetylene gas into the air would not be smart. It's a fuel gas, and it's extremely flammable. Mixed with air in the right proportions, it's going to be explosive. Flammable gases like acetylene or propane are especially hazardous. Gases mix with air very easily, so you have to guard against accidentally releasing them into the air. What's more, they're often stored in compressed gas bottles like this. When these cylinders are involved in a fire, you've got real problems. You see, when a compressed gas cylinder gets hot, a fusible plug right here on the valve blows out. Now that releases the gas into the fire area. And whether it's fuel gas, like acetylene, or an oxidizer, like oxygen, the fire is going to get a lot worse. So you've got to keep these things cool. Now, you can either remove them from the hot area, or you can cool them with a hose line to keep their plugs from blowing. These things are sensitive, so it's even a good idea to keep them away from direct sunlight. Now, I don't want to give you the wrong idea. Oxygen and acetylene are nothing to be scared of, but they do deserve your respect. There are certain dangers involved in their use. One of them is the risk of accidentally creating an explosive atmosphere through a leak or whatever. The other danger is that this equipment creates sparks. Any kind of welding, cutting, or grinding makes sparks. Now that means that these jobs are all potential ignition sources. We group these three jobs, welding, cutting, and grinding, into one category called hot work. Whenever hot work's performed outside of a protected area, you have to take special precautions to avoid starting fires with the sparks. Now, usually these precautions involve a fire watch. The person on watch stands by with a fire extinguisher while the work's going on. He's also responsible for making sure the area is clear of flammable liquids, gases, dusts, and other combustibles. As an added precaution, he should remain on watch for a half hour after the work's finished. If you're going to be doing any hot work, or if you'll be standing a fire watch, make sure you know your company's safety regs. Often you'll have to have a checklist to make sure all of the necessary precautions are taken. Fire safety is never something that can be done halfway. We've learned a lot about fire prevention, both at home and on the job. The main thing to remember is that lives are at stake. Yours, your co-workers, and your families. We've also seen how fires start, what the different kinds of fires are, and how they're put out. And we've seen the correct way to respond to a fire. You have to protect yourself, report the fire, and if you can, put it out, or at least keep it from spreading. Remember, people die every day from fires, both at home and at work. It's really everybody's job to protect people and property from fire, by fire prevention, by reporting fires properly, and by putting fires out. When a fire starts, every second counts. Make sure you know what to do. It could mean someone's life.